Hi guys, this is Dr. J here, and today in this video we are going to learn how to balance oxidation and reduction reactions using oxidation numbers. So I hope that you guys have reviewed all the videos that I have posted on oxidation numbers, and then finally we are going to use those oxidation number lessons that we learned in previous videos in order to balance oxidation reduction reactions. Once again, oxidation reduction reactions are also known as redox reactions in short. So they are both the same thing, okay? All right. So in this video, I'm going to balance 10 different redox reactions. But here's the thing. The first few examples are very easy. Honestly, you don't need to use oxidation numbers to balance most of these reactions, mainly because, those reactions are extremely easy and you can easily balance it without using any method. You can just eyeball it and then balance it. But I'm going to use the oxidation numbers and try to balance the reaction anyway, so that you will learn the technique along the way. Okay, so there is going to be 10 reactions that I'm going to balance in this video, and hopefully you will practice more equations in your quizzes and in your assignments, and then you will be experts in balancing redox reactions using oxidation numbers. Once again guys, in the beginning you might take a lot of time to balance these reactions. Maybe you might take like 5 to 10 minutes to balance these reactions using a redox concept, the oxidation numbers. But once you practice, most of even the most difficult equations can be balanced within like 1 to 2 minutes if you master this technique. Okay, so this technique is not for the simple reactions. Once again, we usually use this technique to balance very complicated redox type reactions, but of course in order to master it you might want to balance these reactions again and again and then perfect your craft. Okay, all right, so let's first talk about the first reaction that I have in here. So I have a reaction between A and B, generating A plus and B minus. So from the first look of it, let me make a small modification to this reaction. I want to make it B2 minus, okay, just to make things interesting. Okay, so A reacting with B, giving you A plus and B2 minus. This is the reaction that we want to balance. And some people might say that, hey, it is already balanced. You have one A on both sides, one B on both sides, so it should be balanced, right? You don't have to do anything. Some people might argue that. But no, this is not balanced. This reaction, even though you have one A in both sides, one B in both sides, this is not balanced, mainly because the charges are not balanced. Charges on both sides are not balanced. So if you take a look at the charges on both sides, in the reactant side, you only have, you have no charge. The charge is zero, okay? Zero charge. In the product side, the overall charge is a -1. So in the reactant side, you have a zero charge. On the product side, you have -1 charge. So the charges on both sides are not balanced. So therefore, this reaction is not balanced. You can't just say that this is balanced because you have one A on both sides and one B on both sides. No, the charges are not balanced. So we have to balance this reaction. To balance it, you can use two different techniques. If you remember, I briefly mentioned about half reaction technique, okay, in previous video, but I don't recommend using that technique because it is a very time consuming process. Instead, I'm going to teach you a new technique using oxidation reduction numbers. Okay, so let's get to it. So first of all, the first thing that I want to do is I want to write the oxidation numbers for each and every atom that is involved. Okay, so for A, the oxidation number is 0. For B, the oxidation number is 0. A plus, the oxidation number is +1. B2 minus, oxidation number is -2. I just used rule number 1 and 2 in oxidation numbers in order to calculate the oxidation numbers. Okay, and now let's identify oxidation and reduction. Okay, so A going from 0 to +1 oxidation state, B going from 0 to -2 oxidation state. For A, during this reaction, oxidation number has increased. For A, the oxidation number has increased, right? So therefore, A has been oxidized. Why? Because during oxidation, the oxidation number is increased. For B, the oxidation number is decreased, which means it is reduction, because during reduction, the oxidation number is decreased. So now you have identified the oxidation and reduction. The next step is actually to determine how many electrons are gained and lost during these half reactions or during this oxidation and reduction. During oxidation, the difference between oxidation numbers is 1. Okay, so the electron difference is 1. For B, for the reduction, the oxidation number difference is 2, going from 0 to minus 2. The oxidation number difference is 2 electrons. Okay, so now we know how many electrons were gained or lost during each of these half reactions. Now we have to make sure to balance these electrons. Once again, the concept here is that every electron that is lost has to be gained by someone else, right? So there is no floating electrons. Okay, every lost electron has to be gained by someone. So to do that, what we do is we try to find the least common multiple for the oxidation and reduction electrons. Okay, so we try to find the least common multiple for oxidation and reduction. So in this case, for 1 and 2, the least common multiple would be 2. So you multiply 1 electron by 2, 2 electron by 1. Okay, so once you have that, you have balanced the electrons. Okay, so which means for oxidation, you need to multiply the half reaction by 2, because we multiply 1 electron by 2, which means you have to multiply A by 2. I mean, B is multiplied by 1, that means you don't have to do anything. So now this reaction is balanced. How do we know that? We can check the charges. Okay, in the reactant side, the charges are 0. Overall charge on the reactant side is 0. On the product side, once again, the overall charge is 0. So the reactant and product charges balance out, and therefore this reaction is balanced. Okay, that is how you balance redox reactions. Let's take another example. Okay, so now I'm going to go to the real world and take examples from the real world. Okay, so in here I have a reaction between magnesium and silver, ion. Okay, so the first thing that we do is what? We write the oxidation numbers for each and every atom involved. Okay, so for magnesium, oxidation number is 0, silver plus 1, magnesium plus 2, and silver metal is 0. So I just wrote all the oxidation numbers that are relevant. And then identify oxidation and reduction. So magnesium going from 0 to plus 2, the oxidation number is increased. So therefore, this is actually oxidation. Okay. And then for silver, the oxidation number is decreased from plus 1 to 0. So this one is reduction. Here is your reduction. So now we have identified oxidation and reduction. What we need to do now is to calculate the electron difference for oxidation and reduction. For oxidation, you are going from 0 to plus 2, so the difference is 2 electrons. For reduction, you are going from plus 1 to 0, so the difference in electrons is 1 electron. Okay, 1 electron. So the least common multiple for the two half reactions, oxidation and reduction, is 2. Okay, so you multiply 2 electrons by 1 electron by 2. Okay, so once again, you multiplied the oxidation side by 1, reduction side by 2. So if it is 1 by 1, don't do anything. If it is by 2, you have to put 2 in front of this silver half reaction. So this reaction is balanced. This reaction is now balanced. Okay, so now you understand what we do, right? So first of all, we write the oxidation numbers of every element, and then we figure out oxidation and reduction. Once you figure out the oxidation and reduction, by using the oxidation numbers, you get the electron loss or gain. Once you have the electron loss and gain, okay, you try to balance the electrons. Every electron that is lost should be gained. Okay, so therefore you have to make them equal. Okay, to balance electrons, you can figure out the least common multiple for both oxidation and reduction electron numbers. In here it is 2 electrons, so you try to make both oxidation and reduction equal to 2 electrons. And if you multiply your half reaction, which is the oxidation or reduction, by a certain number other than 1, you will use this number as an stoichiometric value, okay, as a coefficient in front of that particular species. All right, and then finally you can calculate the overall charge in the reactant side and the product side. So in the reactant side you have a +2 charge. How did I get that? 2 plus 1 is +2, right? In the product side, once again, you have a +2 charge from magnesium. So this reaction is balanced. This reaction is balanced because the overall charge is 0. The overall charge is 0. The overall charge is 0. Let's go to the third reaction. So by now, you should have some idea about how to balance reactions. So from here onwards, I want you to pause the video and then see if you could balance this reaction without my help, okay? So every time when I go to a new equation, I want you to pause the video and try it by yourself. First step is to actually get the oxidation numbers, so which is very straightforward now. These are the oxidation numbers for the 4 species involved. Once you have the oxidation numbers down, figure out the oxidation and reduction. For iron, the oxidation number is decreased, so therefore it is reduction. For zinc, the oxidation number is increased, so that is oxidation. Once you have the oxidation and reduction figured out, get the electron difference. For reduction, the difference in oxidation numbers is 3, so it's a gain of 3 electrons. For oxidation, the oxidation number difference is 2, so that is a gain of 2 electrons. Okay, so you have 3 electrons and 2 electrons as the electron gain and loss, right? Once you have that, figure out the least common multiple for 3 electrons and 2 electrons, which is 6. Okay, so in order to get to 6, you have to multiply 3 electrons by 2, 2 electrons by 3, because the least common multiple for 2 and 3 is 6, right? So reduction half reaction has to be multiplied by 2. Oxidation half reaction has to be multiplied by 3. Now you can verify the accuracy of this reaction by calculating the overall charge. And if you do that, you will realize that both reactants and product side has a +6 charge, and therefore this reaction has to be balanced. All right. Okay, so now we are going into a little bit difficult ones. Okay, so now things might get harder down the road. Okay. All right, so just for the record, guys, most of these reactions may be balanced without using oxidation numbers, okay? But we are trying to practice a technique, okay? That is why I'm starting with a simple reaction, okay? So let's do this one. All right, so first thing that you do is what? You might want to pause the video, try to balance this by yourself, and then start with me, okay? All right, so write the oxidation numbers. -1, 0, 0, -1. There you go, the oxidation numbers. Once you have the oxidation numbers, usually we identify the oxidation and reduction. Okay, let's do that. So bromide goes from -1 to 0, so that is a decrease in the oxidation number, which means it is the reduction. And chlorine, -1 to 0, it is an increase in the oxidation number, so this is oxidation. -1 to 0, you are increasing your oxidation number, so that is oxidation. Sorry about that. And for chlorine, you are going from 0 to -1. So the oxidation number is decreased. So this is reduction. So we identified oxidation and reduction. But after that, you might want to do something new in this reaction. You have to do something new in this reaction. Let me explain you what it is. Okay, before balancing this reaction, if you take a look at it, you realize that in the reactant side you only have one bromide ion, and in here you have two bromine atoms in the product side. So one on the reactant side, two on the products. So that is not balanced, right? So first thing that you do is you will balance bromine without doing anything. Okay, before worrying about the differences in electrons, first you want to balance whatever the species that you have that are being oxidized and reduced. That is a new step that we do. Okay, try to balance the atoms on reactants and products for each element. Okay, we are not trying to balance the whole reaction, but we are trying to balance each element on both sides. Okay, that is something important. So you have one bromine in here, two bromines there, so put two here. That is new. Okay, and two chlorines here, one chloride there, so put two here. All right, so let's try to balance it. So for each bromine, the oxidation number is going from -1 to 0. So the difference is 1 electron for one bromine. For two bromines, it is 2 electrons. Okay, how did I get 2 electrons once again? According to oxidation number, for each bromine, the difference in oxidation number is 1 electron. Okay, -1 to 0, the difference is 1 electron. But we have two bromines, so it is not 1 electron, we have to have 2 electrons. Okay, and for chlorine, the difference in oxidation number is 1 electron, but you have two chlorines on the two sides, so therefore it is 2 electrons. Okay, so this one is simple. Why? Because both oxidation and reduction lose or gain 2 electrons, so therefore it is already balanced. The electrons are already balanced. You don't have to do anything. This reaction is already balanced. This reaction is already balanced. Okay, this reaction is already balanced. All right, let's go to reaction number 5. Okay, you might feel like, in reaction number 4 you don't have to go through all the troubles in doing this. You can easily eyeball it and balance it. But we are learning a technique once again. Okay, so we have to start with simple stuff. Okay, all right, let's balance this one. Once again, you can balance this easily without oxidation numbers. That is fine, but we are going to use oxidation numbers and balance it because we are learning a technique. Okay, write the oxidation numbers down. Now I'm not going to explain it too much. Okay, you should pause the video and try it first. All right, magnesium is going from 0 to +2, so this is oxidation. Oxygen going from 0 to -2, this is reduction. So you take the difference in electrons. Before getting the difference in electrons, now you have one important thing to do. On the reactant side, you have two oxygens. In the product side, you have only one oxygen. So no, you have to balance it first. So put 2 here, okay, which balances oxygens. And in here, you have two magnesiums on the product side, so put 2 here, so that the magnesiums and oxygens are the same in both reactants and product side. So get the electron difference now. Okay, for oxidation, each magnesium has a 2 electron difference, but here's the thing, you have two magnesiums on both sides, so it is not 2 electrons. You have to multiply 2 by 2, which is 4 electrons. For reduction, each oxidation number difference is 2 electrons, but you have two oxygens, so that is 2 times 2, which is 4 electrons. Okay, which is 4 electrons. 4 electron times 1, 4 electron times 1. So this reaction is actually already balanced. Okay, all right. All right, so now we are getting into some important ones. Okay, if you are to balance these reactions using coefficients in the chemical formulas, you might be in trouble. Okay, now you can see that this is a complex chemical reaction. To balance these chemical reactions, you might want to use oxidation numbers. Otherwise, you will spend like 15 minutes to half an hour, and then you might not even balance it at all. Okay, so try to balance this by yourself, and then I will explain it. Okay, first of all, get the oxidation numbers. Get the oxidation numbers. All right, check your oxidation numbers with mine. Okay, hydrogen is +1 in both sides, right? So hydrogen oxidation number is not changed. Hydrogen oxidation number is not changed. So therefore, we don't have to consider hydrogen. Okay, we don't have to consider hydrogen when balancing reactions using oxidation numbers, because the oxidation number of hydrogen is not changed. Look at oxygen, it is -2 all across the reaction. So oxygen is not changing its oxidation number. So let's not worry about oxygen. Okay, let's not worry about oxygen because it is not changing the oxidation number throughout the reaction. But chlorine and manganese, okay, they are changing their oxidation number during this reaction. So these two elements are important, chlorine and manganese. So let's combine them. Let's combine them. Okay, so identify oxidation and reduction. Going from -1 to +7, that is definitely oxidation. That is a huge oxidation. Okay, and then going from +7 to -2. Okay, this is +7, by the way, if it is not clear. Okay, this is +7. Going from +7 to +2 is definitely reduction. Okay, so now you know oxidation and reduction. We identified it. Okay, and then get the electron difference. First of all, check whether you have one chlorine on both sides and one manganese on both sides. Yes, we have, so we are good in that. We don't have to pre-balance anything. Now get the electron difference. So for chlorine, there is an 8 electron difference. That is a lot. Anyway, for manganese, there is 5 electron difference. Okay, 5 electron difference. Wow, that is a lot of electrons moving, right? So the least common multiple for 8 and 5 is what? 8 and 5 is 40. Okay, 40. So to get to 40, you multiply 8 by 5, 5 by 8. You can either use least common multiple, or sometimes, by multiplying each value, I mean 8 and 5 by each other, you can get the answer. Okay, so 8 by 5, 5 by 8, which means you have to use number 5 in front of every chlorine, number 8 in front of every manganese. This is difficult than I thought, but anyway, see, you will almost never guess these numbers if you had to rely on uh, coefficients on the chemical formulas. Okay, that is why oxidation numbers are important. I mean, I'm going to give you like a really nice samurai sword. Okay, by this technique, don't use it to cut your grass. Okay, you can cut, I mean, which means when you have a simple chemical reaction, balance it using the coefficients, and use eyeballing methods, then balance it. But when you have a complicated reaction like this one, then you can use this technique. Okay, all right, so now chlorine and manganese should be balanced on both sides. What we do now is balance oxygens. Okay, balance oxygens. So let's worry about oxygens. In the reactant side, you have 8 times 4. Let me use a different color. It is confusing if I use the same color. Okay, 4 times 8 is 32. 32 oxygens on this side. So in here you already have 5 times 4, which is basically 20 oxygens. How many oxygens do you need more? You need 12 more oxygens, right? So put 12 here. Put 12 on the water side. Put 12 on the water side. Okay, so 12 plus 20 is 32. Okay, all right, and then balance hydrogens at the end. Why did I keep hydrogens to the end? Because H plus is all by itself on the reactant side, so it is easy to balance it, right? It is easy to balance it. Now you know these things, right? Sorry about that. Okay, so you have 24 hydrogens. Okay, you have 2 times 12, which is 24 hydrogens, so put 24 here. This is a very complex reaction, so you might want to calculate the overall charge and see if it is balanced. Okay, so on the reactant side you have plus 24 from the hydrogens, and then minus 8 plus 5 minus 13. So overall you have plus 11 charge. Okay, so in the reactant side you have 8 times 2, which is plus 16, and then you also have a minus 5 from the chlorates. From the chlorates you have minus 5. Okay, minus 5. So overall that is also plus 11. All right, so this is a very complex equation. We balanced it using the technique that we just learned. Okay, all right, and then we also confirmed the accuracy by calculating the charge on both reactants and product side. Okay, once again guys, what we did was we figured out the oxidation numbers for every atom, and we realized that hydrogen and oxygen are not changing the oxidation number, so there is no point of using the oxidation numbers for hydrogen and oxygen, so we let them alone. But chlorine and manganese are changing their oxidation numbers during this reaction. So we figured out the oxidation and reduction, and we got the electron difference. We used the least common multiple to balance the electrons for oxidation and reduction, and then finally we balanced oxygen and then hydrogens. We confirmed the accuracy of the balanced chemical reaction by using the overall charge on reactant side and the product side. All right, so now you know everything there is to know about balancing oxidation and reduction reactions. By using this knowledge, let's see if you could balance this one. Pause the video now and see if you could balance it. All right, so these are the oxidation numbers for iron and chromium in both reactant and product side, and they are the only things that are changing. Okay, all right, so let's connect the oxidation and reduction. I just connected both oxidation and reduction. Iron is being oxidized and chromium is being reduced. Okay, now you should have identified it, and also check the accuracy of your oxidation numbers. On both sides you have one iron, one chromium, so we don't have to pre-balance anything. Okay, let's get the electron difference. Let's get the electron difference. For iron, the electron difference is 3 electrons. For chromate, the electron difference is it is again 3. So oxidation and reduction both have the same number of electrons on both oxidation and reduction, so you don't have to do anything, to be honest. Okay, you multiply it by 1. Perfect. So you don't do anything to iron and chromium. Okay, and now simply balance oxygen now. So on the reactant side you have 4 oxygens, so you need 4 water molecules, and on the product side you need 8 hydrogens, because 4 times 2 is 8 in water, so put 8 H plus. So overall charge, now calculate the overall charge. Okay, so on the reactant side the overall charge is plus 6, because you have a plus 8 and a minus 2, which is plus 8, and on the product side the overall charge is again plus 6. So this reaction is balanced. It looks like it's a really complicated one, but it is very easy to balance if you use oxidation numbers. But if you did not use oxidation numbers, it might take a while, okay? All right, so let's balance number 8. Pause the video now and see if you could do it by yourself. All right. I may have made a mistake. No, I think it's correct. Okay. All right, so let's try to balance this equation. So oxidation numbers of importance are sulfur -2. Let me use a different color. Manganese is +6 in this side and +2 on this side, and sulfur is +4. Okay, so let's identify oxidation and reduction. So sulfur going from -2 to +4, that is definitely oxidation. And manganese going from +6 to +2, which is definitely what? Reduction. Get the electron difference now. Let's get the electron difference now. So the difference in electrons, for sulfur it is 6 electrons. For manganese it is 4 electrons. Okay, so 4 and 6 are the two electrons of interest. And if you take a look at the common least common multiple, the least common multiple for 6 and 4, which is going to be 12. Okay, 12. So 6 is multiplied by 2, 4 is multiplied by 3. Okay, so H2S is multiplied by 2, and then SO2 is multiplied by 2. Manganese side is multiplied by 3. So 3 and 3. Now let's balance oxygens. On the reactant side, you have 3 times 4, which is 12 oxygens. From SO2, you get 4 oxygens, so you only need 8 more. So you need 8 water molecules, which means 16 H pluses. Did I do it correct? Actually, it is not 16. Okay, you might have noticed that I made a mistake. Okay, can you catch the mistake? Okay, 8 times 2, that is 16 hydrogens. 16 hydrogens, not oxygens, excuse me. 16 hydrogens. 8 times 2 is 16 hydrogens. But don't put 16 here. It is wrong. Why? Because you have another hydrogen source right here. You have another hydrogen source. So don't just jump and put 16 right there. You have to account for the hydrogens you have on H2S. Okay, you already have 4 hydrogens, so you only have to put 12 hydrogens. Okay, 12 hydrogens. Is that clear? Okay, so now you can check the charges on the reactants and product side. The overall charge is +6 on both sides, which means this reaction is balanced. If you use oxidation reduction method, you can balance it within 1 to 2 minutes. Otherwise, it might take half an hour and you will still be balancing it. So we are up to the last 2 equations. Okay, so you may try to do them by yourself. Okay, you should try to do them by yourself because I have taught you a lot now. Okay, but let me do this with you. But by now you should be able to try them without my help. Okay. All right, let's do this. First, get the oxidation numbers. Carbon and chromium, those are the things that are changing the oxidation number. I hope you got that correct. Identify oxidation and reduction. Carbon is definitely oxidation, going through oxidation. Dichromate is going through reduction. Okay, and now get the electron difference. Before getting the electron difference, you might want to see that, you might have noticed that you have 2 chromiums here, 1 chromium here. Now you know. Okay, that is why during the simple reactions we put 2 chlorines, 2 bromines in the beginning, even though they are obvious. But this is a complex equation. In here, if you don't balance chromium by putting 2 on the product side, you are going to have a really hard time balancing this equation. Okay, so before doing anything, okay, identify oxidation and reduction and then balance chromium on both sides. That is the most important thing. Reactant side has 2 chromiums, so put 2 there. That is very important. If you haven't done that, erase all you did and then redo this equation. Okay, all right, let's do this. Let's identify the electrons. For oxidation, the difference in electrons is 4 electrons. For reduction, difference in electrons is 3. Why? Because 6 and 3 is the difference is 3 electrons, but that is for 1 chromium. The 3 electron difference is for 1 chromium, but you have 2 chromiums, so actually this has a 6 electron difference. Why? Because on the two sides you have 2 chromiums. Okay, so again we have 4 and 6 as the 2 electrons on the oxidation and reduction. So the least common multiple for 4 and 6 is 12. So multiply 6 by 2, 4 by 3. Okay, so let's do this. 3 for carbon, 3 for carbon dioxide, and then 2 for dichromate, and then this is 2 times 2. Okay, so instead you can write it as 4. Okay, instead you can write it as 4. Alright, so now chromium and carbon are balanced. So let's balance oxygens. On the reactant side, you have 14 oxygens, 7 times 2, that is 14. So you already have 6 oxygens from carbon dioxide oxygen, okay? So 14 minus 6 is 8. So you only need 8 water. Which means you need 16 H pluses. 16 H pluses. Alright, so this reaction is balanced. How do you know it is balanced? You check the overall charge on reactant sides and product sides and it is plus 12. So this is balanced. You don't even have to check again. Okay, this is balanced. Alright, final equation, guys. Final equation. Once again, pause the video and then see if you could balance it without my help. Alright, let's do this. So for carbon, the oxidation number is plus 3. Okay, sulfur plus 6. Carbon dioxide plus 4. Carbon is plus 4. Sulfur is plus 4. Alright, I identify oxidation and reduction. So carbon is increasing its oxidation number. So this right here is your oxidation. SO3 going from 6 to 4, so that is reduction. So sulfur is reduced, SO3 is reduced. Let's get the electron difference. Before doing that, we check both sides to see if carbons and sulfur are already balanced. So you have 2 carbons here, 1 carbon here, so do not forget to put 2 here. Okay, all right, and then sulfur, you have 1 sulfur, so that is okay. So let's get the electron difference. Plus 3 to 4, so only 1 electron difference per carbon, so 2 electrons overall. In the oxidation you have 2 electron difference. For sulfur it is again 2 electrons. Alright, nothing else to do. You multiply it by 1, so carbon and sulfur is already balanced. Count the oxygens. You have 4 plus 3, that is 7. Okay, so 4 plus 2 plus 1, that is 7. Okay, so all you need is 2 H plus ions, 2 protons, and this is balanced. This reaction is balanced, guys, and the overall charge is 0 on both sides. With that, we are going to conclude our video. You guys have a nice day. Okay, let me know if you have any questions. Have a good one, guys.